Hello there. We have a problem in viscous flow, and it's a syringe. There's some fluid in the syringe. It's actually water, and we are pushing. And this part has a radius 1 centimeter, and the needle part is 1 millimeter. And this is the rate at which fluid is supposed to come out. So this is the volume. This is the volume flow rate. So volume rate. And we're supposed to, we're given density and we're given this, and we're supposed to find the force F. So first, I want to review a little bit of this law, which is very hard to pronounce. You know, some French names are really hard. And I looked up and says, it's kind of like over here is like oil. This one pronounced like O-I-L. It's pronounced like that in this part. So Poiseuille, something like that. Poiseuille's law. So Poiseuille's law will be. So it's about. He was a medical doctor, and he wanted to study blood flow through arteries and veins, and he's worked out this formula from his studies. So it's about one tube, and viscosity eta, and the tube radius is r, and the pressure difference is P1 minus P2, and Q is the rate of flow. This is volume rate of flow. Okay, so it's almost like this thing is like Q is like current, and this is like delta P. Delta P is like the voltage, and this resistance is the resistance, if you remember your electric circuits. So this is like that. There's an analogy between these two, and that's why the denominator is, I'm calling it resistance. It's easy to remember if you remember resistance. But just like resistance has a complicated formula, here resistance is a complicated formula. And very important point of this law is that flow, you just look at if I delta P, how much pressure I need is Q times this resistance, which is 8 over pi eta L over R to the power 4. So you can see when if the vein narrows, then the pressure will build up. That's what the physical consequence of this. And because R to the power 4 is going to build up pretty fast. Okay. The trouble with this problem is that we've got a tube of one diameter over here, another tube of another diameter over here, and the question is how I'm going to apply this law to that. And it turns out we need to break this problem up into two parts. Okay, so we'll break it up into the first part. So let's call it point 1 and point 2, and then we're going to do point 2 and point 3. So this is 1, 2, 3. So over here, let's call the pressure be P2. It will be same way pushing, the same pressure is going to push on the other side, right, for this problem. And so this is single, and for here I will have very simply in here I'm going to have P1 minus P2 will be, let's call this Q. It's going to same flow rate regardless of the velocity will be different, right? V3 will be different than V1, and V1 will be same as V2. But if I convert that over here, this two inside here, this V2 will be, let's call it 2 prime. This V2 prime will be different than this V2 over here. Okay, so we have P1 minus P2 equal to the Bernoulli thing, which will be this V1 equals to V2 equals to V1 here, because the area of cross section is the same. So it doesn't make a difference here. So V2 equals to V1, and so half rho V2 square plus rho GH2, this comes Bernoulli, minus half rho V1 square minus half rho GH1. Now this will be 0 here, and then you'll have a contribution this Q times 8 over pi 8R. Let's call this L1, first tube, and then R2, let's call this R1 to the power 4. So we got P2. Now this 2 prime will be same as P2. When I apply over here, P2 prime minus P1, again we'll have a P3. This minus that will be, this pressure 3 will be atmospheric pressure, and it's going to be half rho V3 square plus rho GH3 minus half rho V2 square, V2 prime square, minus, not half here, just rho GH2 prime. And so flow here, viscous flow here, will add, this will go to 0, and then the Q times 8 over pi 8 L2, let's call this L2, this L2 over R2 to the power 4. Now, so what's the relation of P2 and P2 prime? There will be here, this 2 is going to be, let's write down over here, 2 is in the wide over here, so 2 is here and 2 prime is here. 2 prime is inside this and 2 is here. So let's call it P2 minus P2 prime. P2 minus P2 prime will be, now they will be almost in the same place. So L will be, the length L will be close to 0. So I won't have any contribution like that, but I will have contribution like this. Half rho V2 V2 prime square plus rho GH2 prime minus half rho V2 square plus rho minus rho GH2 prime. Now these guys will cancel out, but V2 prime and V2 will be different because of the area of cross section, and so you can convert this half rho V2 prime will be let's call it v2 square. So v2 prime over v2 square minus 1. Now v2 prime is half rho v2 prime, and then this ratio is just a2 over a1. I mean a1 over a2, I'm sorry, a1 is going to be this area versus this area, and this is just radius over radius to the power 4. So it's going to be half, not prime, v2 rho v2 square, radius 1 over radius 2 to the power 4 minus 1. Okay, so we if you add all of these, then we're going to get add all of this, we're going to get when you add all on the left side, p2 cancels p2, this p2 prime cancels p2 prime, and this atmosphere. So p1 is what I want to know, and because to get f, this p1 is f over area 1. So to get f, just add this up. So answer should be f equals to area 1 times sum on right side. So all these things, so we'll get this plus this plus this, and I'm going to write this up, clean it up, write this up, and then find the numerical value. Okay, so we have actually I messed up here. This is kind of not correct because you need to add atmospheric pressure to it before you multiply it. So we can erase this, and there's a little bit more you can actually do to this. For instance, v2 square, you can write this v2 square as 1 over a2 square, a2 v2 square, and this is same as q. So this is q over a2 square. So this is q square over a2 square. Okay. First thing to notice is your R2 is 1 millimeter and R is 1 centimeter. So look at 10 times difference, right? So it's going to be this is going to be magnified. So let's look at just this before I do all of this stuff. L1 over R1 to the power 4 is 5. Keep everything in centimeter, and so R1 to the power 4. R1 is just 1 to the power 4, but L2 R to the power 4 is 6 centimeter over 1, so 10 to the power minus 1 to the power 4. So this is 6 times 10 to the power 4, and this is 5. So you can see I can just ignore this guy completely. Okay. So this you can ignore because such a big difference, and I'm just adding over there. Now over here, look at this guy. This should be to the power 4 here. Okay, so R1 is 1 centimeter, and this is 10 to the power minus 1 and to the power 4. And so this is 10 to the power 4, and this compared to that 1. So I can completely ignore that 1. Completely just ignore 1. Okay. How about A2 square? A2 square will be pi times 10 to the minus 1 square. So this is 10 to the power minus 2 pi. And let's write all the numbers down. And so Q was just 2. That's the Q. Let's do this. 2, 8 times 2, and eta is in centipoise, so this is 0.01 poise, 0.01, and we have a pi, and then that just says 6 times 10 to the power 4, and the other one is half, rho is just 1, q square is just 2 square, and this is flipped over, makes it pi here, and times 100 times when we do 10 to the power 4. So we already see in this particular numerical values given, this will turn out to be 10 to the 4, 10 to the minus 2, factor of 10. So this is like 10 to the power 3. This will turn out to be 4. So this actually, this all cancels, maybe 1. So this is 10 to the power 6. So we can just totally, after we're done with, we can just ignore this, and this is the answer. So roughly is this going to be the answer. And this is 1/3. 2/3 will be 0.6 times 10 to the power 6. And now we add atmospheric pressure to it. So F equals to, so if, let's get a place to work here. So so F we're gonna be pi times 1 centimeter square times 6 times 10 to the 5, and P atmospheric is 1 times 10 to the power 5, and so roughly 2 times 10 to the 6. It's not going to be Newton, it's going to be Dyne, it's going to be gram centimeter over second square. And so this will be 10 to minus 3 to get to kilogram, and this is 10 to minus 2 to get a meter, about a Newton. So this is going to be about 20 Newton. That's going to be the answer. Okay, this was really what a tour de force. A lot of things we did. You notice that whenever you have a change in the cross section of the flow, you are going to get something from Bernoulli. So this is coming from Bernoulli. And this was coming from Poiseuille law. So here, just numerically, this turned out to be not as big as this, but you got to take both into account when you do the problem. We'll do one more problem of Poiseuille's law in the future, because I think there are a lot of details here that you need to master. Okay, if you want to check out more, of course you can go to this website and subscribe to this channel